Hello everyone, welcome to 26th International Conference on Fracture Surface and Structural Integrity. I am Abhishek Mondal from Department of Chemical Engineering, Sapienza University of Rome, and on behalf of my supervisor, Professor Daniela Pilone and Ferdinando Felli, this is my presentation on effect of dispersed particles on TiAl alloys fracture behavior. TiAl are an experimental class of alloys which are characterized by many interesting properties such as high specific strength, mechanical properties, and good oxidation resistance. These alloys attract a lot of interest as a candidate for replacing nickel-based superalloys for selected engine components such as low-pressure turbine blades. General Electric has started using gamma TiAl for producing low-pressure turbine blades for its next Gen X engines, reducing engine weight by approximately 400 pounds and increasing the fuel efficiency. The interest for aerospace application has boosted the research in this field. Since this is an experimental class of alloys, there are issues related to the use of gamma TiAl based alloys. The main issues are production of mechanical components made up of gamma TiAl based alloys have issues related to high reactivity of alloying elements. Then residual stresses and shrinkage cavity formations make the blade design a very critical factor. And these alloys show a ductile brittle transition temperature at about 800 to 900 degrees Celsius, and hence at room temperature they are very brittle. The research is carried out in order to mitigate these kinds of issues. The research activity is divided into three stages. Stage 1 consists of setting up of an economical production process and analyzing of fracture behavior of gamma TiAl. Stage 2 consists of setting up of a casting process to produce dispersion hardness gamma TiAl alloys, analysis of the obtained microstructure, evaluation of the mechanical properties of the composite material, and analysis of its fracture behavior. While stage 3 consists of comparison between the fracture behavior of the plain and the reinforced alloy and consideration about the use of reinforced gamma TiAl for the production of cast blades. This slide shows the alloy composition used for the casting. In the first case, there is no dispersion hardening, while in the second case, nanometric alumina particles were added to the casting, which was 3% of the total volume. After the production of both the alloys, the microstructure was studied. From the images, it can be seen that both the alloys have similar kind of microstructure. The grains that appear plain and white are the gamma grains, while the other ones are the lamellar colonies of alpha 2 and gamma grains. The picture on the right shows the microstructure of the alloy with alumina dispersion. Upon analysis, it was found that the nanometric alumina that was added has a homogeneous distribution, but at some places there are micrometric agglomerations that are represented by the black faces. This slide shows the fracture surface of gamma TiAl. The two images on the left show a cross-section of a turbine blade made with TiAl without any kind of dispersion, while the image on the right shows a specimen with alumina dispersion. We have already published a paper on the mechanical properties of TiAl with alumina dispersion. Based upon that, we can say that the addition of alumina is very effective in increasing the mechanical properties, but at high temperature, that is in the range of above 750 degrees Celsius, which is a favorable thing as these alloys are supposed to work at these temperatures, while it still remains very brittle at room temperature, which is a problem during the manufacturing and production phase. That is why it is very difficult to produce such kind of alloys. Only from this kind of superficial observation of the image on the right, it is evident that the alloy with alumina dispersion is much more brittle than the one without alumina dispersion. Coming to the fracture surface of the alloy without alumina dispersion, we can see that the fracture surface is brittle in nature, that is, it is translamellar and transgranular in nature, which shows a typical cleavage fracture. Also, as you can see from the picture on the right, there are secondary cracks and shrinkage cavities that affect the mechanical properties of this alloy. This slide shows the fracture surface of the alloy with alumina dispersion. Here also the fracture is brittle in nature with translamellar and transgranular tears. But upon a closer observation, it can be seen that there are certain spots where the alumina concentration is higher. These are represented by the white circles. Here it is interesting to see that there are a few pores in the alloy shown by the triangles, which may be due to the detachment of alumina, and these would suggest that the presence of alumina inside the alloy can be the points of stress concentration and crack initiation and propagation. So this explains why the alloy with alumina dispersion is much more brittle than the alloy without alumina dispersion. Also, there are some secondary cracks shown by the rectangle present inside the material, which again promotes these kinds of brittle fracture. Apart from these issues, by observing the fracture surface, we can also highlight that there are also shrinkage cavities present in the alloy with alumina dispersion. Upon closer inspection, it can be noticed that inside the cavities there are a particular kind of crystal shapes represented by the circles, which we think is formed due to the addition of alumina. The presence of these crystal shapes, characterized by the presence of edges, could also affect the behavior of the alloy, but we need to study more about their nature, their formation, and their effect on the alloy. These kinds of structure are not present inside the cavities of the alloy without alumina dispersion. So finally, it can be concluded that the research carried out in this paper highlighted that although dispersion hardening allows to increase the mechanical properties of gamma TiAl base alloy at high temperature, the presence of dispersoids affect the fracture behavior of the alloy. And the presence of dispersed particle that represent a discontinuity in the metallic matrix favors crack propagation and increase in brittleness of the alloy at room temperature. Finally, a further study is required to optimize shape, quantity, and distribution of the dispersed particle with the aim of increasing fracture toughness. With this, I finish my presentation and thank you.